1 plus 1 equals 2. If there is one thing people feel absolutely certain about in mathematics, it is this. But are we really sure it is that simple? Let's pause for a moment and think about it. What do we actually mean when we say 1? What exactly is 2? And how do we define addition? Intuitively, we all know what these ideas represent, but giving them a fully rigorous definition is not simple at all. A first attempt might be to say that 0, 1, and 2 are elements of the natural numbers, and that the natural numbers are, well, 0, 1, 2, and so on. But this explains nothing. It is a circular definition. How do we break out of this circle? If we could define the natural numbers from scratch, in a precise and rigorous way, the problem would be solved. And one of the first people to manage this was the Italian mathematician Giuseppe Peano, who formulated 5 axioms that now carry his name. Let's go through them one by one. First axiom: there exists a natural number called 0. Here, 0 is just a name. It is not yet the number we know. It is simply an element that we decide to call 0. In fact, in many formulations, 0 is not even included among the natural numbers. Second axiom: every natural number has a natural successor. More technically, there exists a function called the successor function, and usually denoted by s, that assigns to every natural number another natural number. Third axiom: different numbers have different successors. In other words, the successor function is injective. Fourth axiom: 0 is not the successor of any number. There is no natural number whose successor is 0. Fifth axiom: the axiom of induction. If a set of natural numbers contains 0 and also contains the successor of every one of its elements, then it must contain all natural numbers. These 5 axioms do not tell us what the natural numbers are. They tell us what structure any system must have if it is going to behave like the natural numbers. Now imagine a sequence of completely abstract elements: 0, A, B, C, and so on. At this stage, they do not represent quantities. They are not 1, 2, or 3. They are simply objects with no intrinsic meaning. The only thing we know about them is that they exist, and that there is some kind of direction connecting them. This direction is described by a function, the successor function, which we denote by s. So we have s of 0 equals a, s of a equals b, and so on. Nothing here yet resembles the idea of a number. We are not counting, we are simply organizing a structure. Now something important happens. We can interpret this structure in a conventional way. We take the element that comes after 0 and we call it 1. The element that comes after 1 we call 2, then 3, 4, and so on. By assigning these names, we recover exactly the intuitive idea of the natural numbers, but now built from a rigorous logical foundation. With this setup, we can finally define addition using 2 simple rules. Rule 1: a plus 0 equals a. Rule 2: a plus the successor of b equals the successor of a plus b. These 2 rules allow us to compute everything, so let's compute 1 plus 1. We know that 1 is the successor of 0. Using Rule 2, 1 plus 1 is the successor of 1 plus 0. And by Rule 1, 1 plus 0 equals 1, so 1 plus 1 is the successor of 1, which we call 2. This gives us a formal proof that 1 plus 1 equals 2 in this particular system. But is the successor function unique? Here is where things become really interesting. We define the natural numbers as any structure that satisfies the Peano axioms. But the axioms never tell us exactly what the successor function must look like. They only describe its properties. This means that different successor functions can satisfy the axioms, and therefore there can be different ways to realize the natural numbers. For example, look at this successor function. It satisfies all of Peano's axioms. And so does this other one. Of course, not every function works. For instance, the identity function fails. It sends 0 to 0, violating the fourth axiom. And any function that assigns the same successor to two different numbers fails the third axiom. But among the functions that do satisfy the axioms, unusual things can happen. Let's compute 1 plus 1 using one of these non-standard successor functions. In one such structure, 1 plus 1 turns out to be 4. If we change the successor function again, even stranger things happen. 1 can be seen as the successor of 2. 2 as the successor of 0. And when we compute the successor of the successor of 1, we obtain 5. So, is 1 plus 1 really equal to 2? Yes, and also no. The equality holds if we choose the standard successor function, the one that matches our everyday intuition. But the Peano axioms allow many other structures, and in those structures, the objects we call 1, 2, successor, or sum can behave very differently. In mathematics, truths do not fall from the sky. They always depend on our definitions, our axioms, and the structures we decide to study. If we change the structure, the rules of the game can change as well.